Yeah, so today I will discuss shifts on locally compact Hausdorff spaces, but quite briefly. But at least we will formulate the theorem about the what's going on. Is it okay? Okay. Consider some locally compact Hausdorff space, and consider some presheaf with values in dualizable categories. For example, it might be a constant presheaf, but I want to just assume that the value on the empty set is 0 just for convenience. And then the statement will be the following. So I will formulate it for universal localized invariant, but in particular, it follows for any finitary localized invariant. So when you consider this universal localized invariant commuting with critical limits applied to shifts, you get compactly supported cohomology of X with values in, like you take your log of these categories. So you get a presheaf, then let's use this notation for shiftification. So you take shiftification and you take compactly supported sections. In particular, the same holds for K-theory or any other finitary localized invariant. And maybe before commenting on this, let me prove some very simple statement about compact objects in this category. It's not really necessary for the proof, but it's useful to know what are the compact objects, and in particular to see that this category is usually not compactly generated. So the compact objects, consider some object in this category of shifts with values in C, and then I will, but I mean, I think everyone knows what a shift is. I mean, Thomas. Yeah, I mean, you have these restriction functors, but Dustin, I think you know what is a sheaf of modules over a presheaf of rings. So yeah, this is just a straightforward generalization of that notion. Okay, so you have these restriction functors, and basically you require descent. When you formulate descent conditions, you just take the right adjoints. So like the condition is, for example, that for any u and v, you have this Cartesian square f of u union v to right adjoint of the restriction applied to f of u, right adjoint of the restriction applied to f of v, and right adjoint to the restriction applied to f of intersection. So you want this to be a pullback. Sorry? R, yes, yeah. So pullback, of course, in C of U union V. So let it be, so this is the second condition. The first condition is that f of the empty set is 0. And the third condition is that f of u is the inverse limit over v compactly contained in u, way below u, of this right adjoints of f of v. So just the usual stuff, but yeah. So if C is basically categories of modules over some presheaf of ring, then this is what everyone knows as sheaf of modules over a presheaf of rings. Yeah, yeah. No, but I guess you know what is a quasi-coherent sheaf on a scheme, and then you need to know what is a sheaf over a presheaf of rings. So, sorry? Okay, okay. Uh, yeah. No, the category of shifts will be actually the same. I mean, yeah, you would need to show this, but yeah, it's actually the same. It's actually equivalent. But I mean, there is no reason to shiftify the presheaf of categories. I mean, the result might be complicated, and it's just an unnecessary complication. Yeah. So. All is true for what? For who's? Yes. For arbitrary Grothendieck topology. Yeah. You can generalize here. Yeah. Okay. So I wanted to formulate this simple statement about compact objects. So consider some sheaf with values in C, and then the following are equivalent. That F is compact. And the second is that, first of all, we of course need to require that F has compact support. And that F is locally constant, but precisely it means that F can be covered by subsets U such that F restricted to U is just this constant sheaf. So P sub U, where P is a compact object in C of U. And let's just prove this immediately. Well, I will prove that. Well, I assume that 2 implies 1 is kind of easier. Well, exercise, let's say. But the interesting direction is that 1 implies 2. And for this, you just observe that. So step 1 is that suppose that a stock at some point vanishes. So this is like 0 object of CX of the stock of the presheaf of categories. Then there is a neighborhood U of this point X such that F vanishes, the sheaf itself vanishes in the neighborhood of this point. Colimit of categories, yes. In cut dual, in dualizable categories. Oh, yes. Or the same as in parallel, yes. Yeah. And this is simply because this assumption that the stock vanishes implies that F is the colimit over V, which are compactly contained in the complement of this point of JV lower shriek, JV upper star of F. And so F must be a direct summand. So hence F is a summand of some sheaf of this form, which of course lives outside of the neighborhood of. So this implies that the restriction of F to X minus the closure of V is 0, and X minus the closure of V is the neighborhood of our point. So this is kind of automatic. We use compactness of F, of course. And step 2 is that suppose we have a situation when our stock doesn't vanish at some point, then it must be a compact object in C sub X. just because pullback to the point is, of course, a strongly continuous functor. And it follows that there exists some neighborhood of this point such that this stack can be lifted to some compact object of C of U. Just because taking compact objects commutes with filtered colimits. I guess this is the exercise which we didn't do, but yeah, okay, yeah, exercise. Taking compact objects from dualizable categories to small categories, this operation commutes with filtered colimits. Yeah, so you can lift this stack to a compact object of C of U, and then we get no, it's just more or less apply one of your 10 or 11 definitions and just to choose convenient definition and yeah, and be happy. Yeah. I mean, it's not difficult. It's yeah. There is a functorial resolution by compactly generated categories, and you can just use this functorial resolution. Yeah, we get a map of sheaves. Let's call it okay, shrinking U if necessary. We get a map of sheaves P sub U to F. So a map of sheaves on X. So P sub U means that we extend by 0 this constant sheaf of U. Let's call it phi. Sorry, yeah. Yeah, so we get such a map. Then choosing some neighborhood of V, some neighborhood V of X, which is compactly contained in U, we get that cone of phi restricted to V bar is a compact sheaf on V bar, on the closure of V, with values in C restricted to V. This is compact objects. And so by step 1, it vanishes in some neighborhood W for some W containing X. And so we win, right? So we prove that it is locally constant with compact. So locally it can be written as a constant shift coming from a compact object of some C of U, where U is this W. And then step 3 is just trivial to see that it has compact support. It's basically follows from step 1 if you consider one point computation, but explicitly we know that F is a colimit over U which are compactly contained in X, which means that they can have compact closure of JU lower shriek, JU upper star F. And of course, each of these guys has compact support, and F is a direct summand of some sheaf of this form, and so we see that support of F is compact. So this is a crystallization of compact objects in this category of sheaves in this generality for this non-constant coefficients. And now let me briefly explain how to compute localized invariance. So first, maybe let me remark that there are some proofs, including the proof given by Dustin and also the proof given by Mark in the notes. They use the hypercompleteness argument, which require the following fact. So the following fact, if we want to prove them in this generality for universal classical invariant, So the following fact, which is that there exists a conservative continuous functor, limit preserving functor from motifs, localizing motifs to spectra. And this is true, but this is non-trivial statement. Like it follows from dualizability of mod log, which follows from rigidity, which I hope to explain. I think on Friday, follows from rigidity of this category of localized motifs. But this is kind of non-trivial fact, and so I just want to sketch a proof which doesn't use any knowledge of this sort, which is like the proof which I originally gave, but I think just Mark didn't understand it when he made the notes. So basically what you do is, let's make some notation. So this sheaves, category of sheaves, is contained in the bigger category, which I like to call continuous presheaves. So these are presheaves satisfying condition 3 only. Satisfying condition 3. And then, and also let me just mention that when you are dealing with such categories, it is very convenient to use the concept of k sheaf and k presheaf, which means that let's first start with continuous k presheaves. This means that we first left can extend our presheaf of categories. So for compact y in X, we just say that C of y is the colimit over U containing y C of U. So just left can extend our presheaf. We can left can extend for to all locally closed subsets, which is convenient, but in particular to compact subsets. And now these are like presheafs defined on compact subsets. With additional continuity, means additional condition such that the value on some compact subset is the colimit over bigger compact subsets which contain a neighborhood of y of a restriction from z to y of f of z. So the limit is replaced by a colimit, and basically this this functor, if you have some, so if f is the usual presheaf, so usual presheaf, you associate to it the functor which sends, a section of this Cartesian fibration which sends y to the colimit over u containing y of restrictions of f of u. And the inverse functor is given by taking the limit, and you replace restrictions with the right adjoints. And then it's slightly more challenging. No, I mean, this is quite straightforward, but then it's slightly more challenging to show that it gives you also an equivalence when you consider k sheaves. So k sheaves is basically you require additionally finite descent. So this equivalence between continuous presheaves and continuous k presheaves induces an equivalence on sheaves and k sheaves in this generality. I mean, for constant coefficients, this is due to Lurie, of course, and then this category doesn't have to be stable. There are some weaker assumptions which are sufficient, but if you consider stable categories, then you can basically just all you need is just to know that restriction functors are strongly continuous. In particular, this applies to dualizable categories and strongly continuous functors. Okay, so this is just very convenient to do this replacement. And now, yeah, let's return to this board. Now, let me just formulate kind of an exercise, which is quite instructive. You log, when you compute, you log for continuous key presheaves, which is the same as continuous presheaves. You basically get the direct sum over V in X, which are open compact. You consider open compact subsets of U log of C of V. So you get this funny answer where you have this direct sum over all open compact subsets. For example, if X is non-compact and connected, then you get 0, because we assume that for empty set it's 0. But in general, you get this answer. And hint, use tautological semi-orthogonal decomposition for presheaves without any conditions. So K presheaves X C, it has a tautological decomposition into C of V, where V runs over all. We consider K presheaves, so C of Y, where Y is compact. So Y in X is compact. And when you mod out K presheaves by continuous presheaves, then you get similar decomposition, but now you just ignore the open compact subsets. C of Y, such that Y in X is compact, but not open. And the quotient functor is compatible with these decompositions. And so what is left is this direct sum over open compact subsets. And then if you know this, so next step, approximate the category of sheaves, let's say K sheaves, by very nicely behaved finite limits of these categories of continuous K presheaves on various closed subsets. Assuming for simplicity that X compact, because we could assume this from the beginning. So more precisely, if this assumption that X is compact just basically sheaves on, in general, sheaves on X is just the same as sheaves on one-point computation with values in the extension by 0. This presheaf. And so you approximate by very nice finite limits of these categories, and basically, if X is a finite union of Y1, etc., Yn, then if you use this notation that Yi is the intersection of Yi for I non-empty, then what exactly? Right, the very right board, yes. Which one? Which of them? Lower, yeah. What exactly do you want? But I mean, there's a lot of stuff. The main statement is that a universal classical invariant of the category of continuous K presheaves is a direct sum over open compact subsets of log of the values of our preshifts on this subsets of C of V. And here it was a hint how to do it. You first do it for preshifts without any conditions, just because category of preshifts has the same orthogonal decomposition. And then you do it for the quotient of preshifts by continuous K preshifts. It also has the same orthogonal decomposition. Sorry? In the first case, it's decomposition into C of Y, where Y is compact. And this is the second case, decomposition into C of Y, where Y is compact but not open. Yeah. Okay, so yeah, so if you have this cover of X by finite number of compact sets, you consider their intersection, and you consider this. You consider this approximation given by such cover. So approximation is basically the limit over this non-empty subsets of dualizable limit, which is the same as naive limit of continuous K preshifts on the intersections. And then, for this approximation, you can easily compute the localized invariant because it's iterated pullback of localization. And then the colimit over all covering sieves, over all such covers, when you make this further refinements, the colimit will be just the category of shifts. So you basically, so essentially, we categorify Czech homology. But Czech homology computed using covers by compact subsets instead of open. Yeah. So yeah, that's basically a more or less straightforward way to compute this localized invariants of shifts. So you just approximate them by something which is computable, and then you just take the colimit. Okay. So that's what I wanted to say very briefly about shifts. And now I want to no, I mean the pullback restrictions to open subsets are not strolling continuous. So I couldn't even take such diagram. Yeah. So that's actually yeah. Actually, just when I started to think about it some time ago, my first thought would be just to clarify the Czech homology, but then I realized that this doesn't work. So the second thought was just take covers by compact subsets, and then it's just straightforward. Okay. So now the next subject will be the internal home in the category of dualizable categories. So this is quite difficult. I mean, just already when you start to think about it, if you try to describe it, to give some description, you see that first of all, it's quite different from the usual internal home in PRL, and then yeah, it's really tricky to obtain any reasonable description when you just start to think about it. And I guess in general, it's just impossible. I mean, there are some descriptions, but you cannot really control anything. But what I will try to explain is the following statement about a class of very nice situations where you can effectively control this internal home. So basically, let's work over some rigid base, rigid symmetric monoidal category. I mean, large stable categories, as Thomas explained. Yeah, so rigid presentable stable category, which is in particular dualizable. and consider some dualizable categories over C. A and B are dualizable categories over C, so relative to C. And suppose that A is proper and omega-1 compact. So let me mention here that A is proper. So this means that evaluation functor from A is something here. From A tensor A dual over C to C is strongly continuous. And when you're working over rigid base, in fact, all this right adjoint will be automatically C linear. And omega-1 compact under these conditions, it means that co-evaluation, if we already assume that it's proper, then omega-1 compactness would mean that co-evaluation of the unit, which is an object of A tensor A dual over C, it must be omega-1 compact. It's basically equivalent. So this is the assumption on A. Then I will explain that for any uncountable cardinality kappa, regular cardinality kappa, in particular for omega-1. If you take this universal classic invariant kappa, universal classic invariant commuting with kappa critical limits, applied to this internal home, dualizable internal home from A to B, this is the same as internal home from the universal classic invariant of A to universal classic invariant of B. So this isomorphism is in the target of this universal localized invariant of categories over C commuting with kappa filter limits. Okay, this is like the first statement, and the second statement, if additionally the base is compactly generated, and it's a little embarrassing that I still have to use this additional assumption, but it's really tricky. So if C is compactly generated, then you can say the same about localizing motives for kappa equals omega. So just U log continuous of this internal home. Is the internal home between the universal localized invariants. So now this isomorphism is in mod localizing motives over C. So universal, the target of the universal localized invariant of categories over C. Yeah. Yeah, but this internal home exists. This particular internal home exists. Yes. Yeah. And first of all, I didn't explain anything about internal home, so it looks quite abstract. But let me just formulate a special case of this. So corollary of this will be that if R is Noetherian commutative ring, the Noetherian condition is just to simplify the derived completion. There is no real reason to assume this, but just for simplicity. And I is some ideal, then when you take this slightly different version of nuclear category for this adic ring, then its continuous K theory will be what was usually called the continuous K theory of a formal scheme, which is the inverse limit of K theory of R mod I to the n. Yeah, and also, yeah, again, we didn't yet discuss this Kashif's head, but also another implication is that if X, let's just say for simplicity that it's a topological manifold, C0 manifold. I mean, of course, this is kind of too strong condition, but just to simplify matters, C0 manifold countable at infinity. Then for this category Kashif's head, which I think Thomas will discuss in the next talk, you have this computation that continuous K theory of Kashif's head of X with values in some dualizable category C. This is Borel-Moore homology of X with coefficients in continuous K theory of C. Yeah, so I mean, special cases of this abstract statement are the categories of nuclear models, well, their version of nuclear models, and the category of Kashif's head, completed Kashif's. So yeah. Yeah. No, I think this is unprovable, meaning that it's either just plain wrong, which is most possible, or there's a model of ZFC where it's wrong. But I think the first case is the case here. I didn't construct a counterexample, but I just think that it's wrong. Yeah. What is the dualizable internal home? Yes, that's what I'm going to do. Yeah. Yeah, and of course, to explain this, I mean, this is quite general, and of course, I will try to explain this just simplifying the assumptions, because it will be already quite difficult. Well, I mean, for Noetherian, any ideal is finitely generated, but yeah, so of course, yeah, and just replace completion with direct completion, and yeah, it's just for psychological yeah reasons. Yeah, there is no yeah. Well, not any. I mean, this will be true for a localized invariant which commutes with countable products. So I use this property of K theory, but yeah. Yeah, there is a more precise statement of this sort. Okay, so yeah, let's try to understand what this dualizable internal home is. So basically, so consider suppose that our base category is just modules over some ring. Modules over K, where K is infinity ring. You can even assume that it's a usual discrete ring or a field. Yeah, it doesn't really matter for the argument. And suppose that our categories like A is modules over some R, over some E1 ring, E1 algebra R over K. So R is E1 algebra over K. And B is also, let it be just modules over S. So both R and S are E1 algebras over K. So our assumption that A is proper is just saying that R is a perfect module over K. And then it's automatically omega-1 compact. So the second condition that omega-1 compactness is automatic. So what is this dualizable internal home? So the natural question is, what is dualizable internal home, at least under these assumptions? Okay, from mod R to mod S. And here, first, even without any description, we know that it exists just because we know presentability of the category of dualizable categories, and we know that tensor product preserves colimits. So we know that it exists, and the question is how to describe it. And basically, we use the following adjunction. Between dualizable categories over K and presentable categories over K, which are, let's say, omega-1 presentable. So there are adjoint functors. One of them is inclusion. So the left adjoint is the inclusion, and the right adjoint is basically the right adjoint sends category. Sorry, C is a bad letter. Let it be E. C is already reserved. It sends E to int completion of omega-1 compact objects in E. So basically, if you instead of dualizable categories, you consider just compactly generated categories, then this is the same as PRL omega, and then this is kind of standard adjunction. So more generally, for any pair of regular cardinalities, you can write down this adjunction, but it's an interesting fact that here you can replace PRL omega with this larger category of dualizable categories, and still this adjunction holds. And it's basically a good exercise just to write down unit and co-unit. And actually, Maxim Ramsey proved an interesting result that this is comonadic adjunction, which is not obvious, of course, just because to prove this, if you use Lurie-Barbek theorem, you would need to deal with limits in dualizable categories. So already you have to be very careful to prove such statements. Yeah, but we will not use that it's comonadic. We will just use that there is such an adjunction, which is already very good. And then basically, essentially a corollary of this adjunction okay, let's say more precisely, if you know that the internal home exists, and if you know this adjunction, then you just immediately deduce that corollary that dualizable internal home from from modules over R to modules over S. This is the kernel, but taken in dualizable categories, like a fiber in the category of dualizable categories, from int completion of the category of bimodules of R mod S omega-1 to int completion of the countable Calkin category of R opposite tensor S. Yeah, and sorry. I'm sorry for confusion. Basically, more precisely, this is representations of R in the countable Calkin category of S. And here, this is just the same thing as representations of R. This countable bimodule. So this is the same thing as representations of R in countable represented modules over S. Just because of our assumptions that R is perfect over K. even if R was just countable represented over K, then it will be still be the same. Yeah, so you take int completion of some category which is small but not exactly little, right? So it has countable sums, and the target is also a category of a similar size. Yeah, so int completion of a category of a similar size, and basically in general this dualizable kernel, it's also difficult to control. But here, under our assumptions, a miracle happens. So crucial fact is that this functor from representations of R in counter-represented modules to representations of R. Yeah, all these representations are k-linear over the base of R in the Kalkin category, countable Kalkin category. That this is a homological epimorphism of small categories. How much time do I have? Not many. Yeah. Yeah. I think I will give some more details tomorrow. But basically, recall if we just want to show directly that a functor, let's say D to E in cut perf is a homological epimorphism, then we need the following for any. So let's call it F. So we need that for any objects X and Y in E. If we consider this contravariant functor in D, which is home, by saying home, I mean spectrally enriched home. So it's a spectrum of maps in E from F of something to Y. You take tensor product over D. I'm sorry, this might be unusual notation, but I will clarify what I mean. You take the tensor product of this with home from X to F of something, and this must be the same as home in E from X to Y. And now what I mean by this tensor product is that, well, okay, it's not only a spectrum, it's a K module. But okay, it doesn't really matter. So the left-hand side, I consider it as a int object of D. Basically, if you have some k-linear category, then contravariant k-linear functors to k modules is just the same as int completion of this small category. And then, sorry? Yes, yeah, of course. So this is like an int object of D, and the right this guy is basically an object of int of the opposite. And I just mean the tensor product. I mean over D. I just mean that we take evaluation. In this case, to k modules because it's everything is k-linear. I mean, I'm just used to thinking about this int objects as kind of modules over the categories. Then it's just the product of a right module with a tensor product of a right module with a left module. And this is useful point of view if when you do such scary. Well, this is not so scary, but this will be scary. I promise you. So yeah. So yeah. When you do such computations, it's useful to you to think about this as like right module and left module. Yeah. Okay. So now I will not give you detailed computation today, but I'll just mention some categorical statements which I use, which you can try to prove as an exercises. Anyway, we will discuss them tomorrow. So I use the following fact. fact 1. Suppose that D is a compactly assembled presentable category, not necessarily stable, or at least assume that strong KB5 holds, and also AB6 for countable products. That filtered K-limits commute with finite limits. In fact, you only care about pullbacks because there's no problem with final objects. Yeah, this is a strong KB5. Yeah. So you assume this, and so let I be a directed partial ordered set, and let F be a functor from natural numbers with the opposite order cross I to D. Then, when you take the limit over n of co-limit over I of f of ni, then this is naturally the same thing as co-limit over order preserving maps from natural numbers to I of limits over pairs n less or equal to m. So this is pairs n less or equal to m is just the twisted arrow category of natural numbers of f of n phi of m. So this n less or equal to m, such a pair is considered as an element of n opposite cross n, natural numbers opposite cross natural numbers. So this, I think, is more or less standard, at least when the target category is like spaces or spectra. I think this is what people encountered in different situations, at least some people. And the second fact is kind of more inhuman. So so let D be as above, and let I and J be directed partial ordered sets. And let's take a functor, but now it will have 4 arguments: natural numbers opposite, cross n opposite, cross I, cross J. Again, to our category D, it's fine only these assumptions. Then and we make assumptions. So assume, like the first assumption will be when you take limit over n, and there are different versions, but I'm taking the actual limit, not the project. Limit over n, limit over co-limit over I, a limit over k, co-limit over j of f of nkij. I want this to be the same, so there's natural map, and I want it to be isomorphism to a limit over n, a limit over k, co-limit over I, co-limit over j, f of nkij. Like in real life situations, you can actually put the first limit in quotes. So like requires that it's equivalence of pro-objects, but it's sufficient to have this. And second is same with where you interchange the roles of n and k and I and j. And the conclusion of this, then if you are interested in computing the limit over n of co-limit over I, co-limit over j, f of n ij, then this will be the same as co-limit over pairs of maps. So you take phi from natural numbers to I, and psi from natural numbers to j, of then limit, inverse limit over n less equal m, inverse limit over k less or equal L of f of n k phi of m psi of L. There's always a natural map from right to left, but it will be isomorphic under these assumptions. And just if you want just to understand how one can possibly prove this, the statements of the sort, it's useful to do the following exercise. Just let me formulate it here. I mean, if you succeed in proving the exercise, then you will be able to prove such statements when the number of arguments is 6, 8, 10, and so on. Yeah, so exercise, so part 1 is prove a version of fact 1, where this natural numbers opposite cross I is replaced with a Cartesian fibration let's say E to N, sorry, to N, yeah, to N. Okay, let's say co-Cartesian fibration over N opposite with directed fibers and cofinal transition maps. Cofinal transition maps, and then you can figure out a similar statements. Instead of order preserving maps, you will just take sections of the dual Cartesian fibration. And the second, let I, J, C, and F be as in fact 2, but without the assumptions. Don't assume anything. Oh, sorry. C is D. Yeah, yeah. The target will be the same. Category with the same assumptions. D. Then, without assuming anything on this functor, we have limit over n, co-limit over I, limit over k, co-limit over j. Is just of f of n k I j. This is the same as limit over the same pairs of maps from natural numbers to I and from natural numbers to j. But now you take the inverse limit over like n less or equal m, less or equal k, less or equal L. So this nm, this nm kl lives in n opposite cross n opposite cross n. And you take f of n k phi of m psi of L. So this doesn't require any assumptions on the functor. And if you understand this, then you will stop being afraid of fact 2. So that's yeah. Okay, I think I'll stop here.